Hi, I made an electronic Etch-A-Sketch without using a microcontroller. Well, it's not actually a real Etch-A-Sketch, of course, but it kind of works like one. Except instead of using pulleys and belts, it uses electricity and wires. And instead of gray aluminum powder, my screen is made of LEDs. I still have to work out a better way to erase the screen, though. After I released my last video, I worried if I'd ever have a good idea for another project or not. Then one night, while my wife and I were watching Star Trek, it came to me. I could make an Etch-A-Sketch.
We already have one.
But if I made my own, it would light up and use electricity.
Oh, wow. Flashing lights. That makes everything better.
Obviously, she was sold on the idea, so now I was committed. The whole circuit design popped into my head fully formed moments after I had the idea. Okay, maybe not the actual wiring, or which parts to use, or how to actually hook anything up. But it was a start. Since the screen was probably going to be the biggest hurdle, I needed to start by deciding how big it would be and how it was going to work. The RAM chips I have can hold 256 values, so I decided a screen made up of 256 individual LEDs might be workable. That'd make a nice 16 by 16 display if they were all arranged in a square, and the whole screen could fit into just one RAM chip. I didn't have 256 LEDs, but I knew that LED matrix display modules existed, so I ordered a cheap package of 8x8 displays to play around with. Then I had to wait for them to show up. But they did finally arrive. The modules I got had a small board attached with a serial interface designed to be driven by a microcontroller. I wasn't sure how to talk to it with the discrete components I was planning on using, so I decided to remove the board and just use the LED part directly. The LEDs in the module are connected in a grid arrangement. To light a particular LED, I need to close a circuit between the row and column that intersect it. So for a single 8x8 display like this, I could address any one pixel with two 3-bit addresses, one for vertical and one for horizontal. I tested the addressing idea by connecting all of the rows on a display to a 3 to 8 decoder. This chip converts a 3-bit input into 8 individual high or low outputs. So depending on the combination of the inputs, only one of the 8 outputs will be active at a time. With the 8 outputs connected to the 8 rows of the display, I can change which row lights up using just 3 jumper wires connected to high or low signals. While experimenting, I was selecting the entire row, but I knew that with a second decoder or demultiplexer chip of some kind connected to the columns of the display, I should be able to turn an individual LED on or off. You might have already noticed, but this technique has a serious limitation. It can only light one LED at a time. In order to display an image, like an Etch-A-Sketch should, it needs to be able to have more than one LED on at the same time. So I expanded my plan to include a timer circuit for refreshing the screen. It'll work by displaying bits from the RAM 1 pixel at a time, hundreds of times per second. And with any luck, our normal persistence of vision will be enough to make it look like a solid image. In order to refresh every LED on the screen, I'll need a 555 timer and a binary counter that can loop between 0 and 255. Now that I have a rough idea of how to approach the screen, I need to figure out how input is going to work. A real Etch-A-Sketch has a cursor that's always at some position horizontally and vertically, so I need a circuit to keep track of that. Since I plan on having a 16 by 16 screen, each axis of the screen can be represented by a single 4-bit number. So to track the horizontal and vertical positions of the screen, I can use 2 more 4-bit counters. Instead of chaining the counters together like in the refresh circuit, I'll increment or decrement one or the other, depending on which way each of the knobs are turning. Of course, that means I need a way to detect which way the knobs are turning. I thought maybe I could use variable resistors since they turn and are, well, variable. These small ones wouldn't be very convenient to use, though. Maybe something like this could work. But I wasn't sure how to convert variable resistance into digital signals for the rest of the circuit, so I did a little more searching online. That's how I learned about digital encoders, which look an awful lot like a potentiometer at first glance, but they work fundamentally differently. There are essentially 2 switches in here that are slightly offset from each other, and the knob is connected to like a disc with a little bump or hole on it. And so as you rotate the knob, the disc with that bump hits switch A, which turns on briefly, and then it hits switch B, which turns on briefly. And And if you turn the knob the other way, B turns on first and then A. So that's how you can tell the direction. These encoders also have a push button input that can be used to select things, or whatever, when you push down on it, which might be handy. I wanted to get a better feel for how this might work, so I hooked one up to a flip-flop and some LEDs. If you look closely, you can see the slight difference in the timing of the blinks when I turn in different directions. The top two lines are the A and B signals from the encoder, and the bottom line is the output of the flip-flop, which is tracking the clockwise and counterclockwise direction. The bottom line is high when turning one way, and then changes to low when rotating the other way. And you notice how the A and B signals pulse in relation to each other as I turn the encoder, and then when the direction changes. I still wanted to validate the idea of controlling a counter with the rotary encoder, so I made a small circuit to test it. The counter goes up or down depending on if the direction signal from the flip-flop is high or low. And it kind of works, but not very well. It keeps missing digits, or jumping and looping or something. I eventually realized that there was nothing magical about a rotary encoder, it's just a complicated pair of switches, and switches are always bouncy. This isn't going to work without some debouncing. So I hooked up some debouncing circuitry, but I discovered that I had to do it for both the A and B signals, which is pretty obvious in hindsight. But that means that one rotary encoder needs two separate debounce circuits just to get a clean output. Since I'll be needing two knobs on my Etch-A-Sketch, I'm going to need at least 4 debouncing circuits. And if I want to use the push buttons, I'll need even more debouncing circuits. It really bugged me how many extra components and how much board space just debouncing the controls was going to take up. So I did some more searching to see if there were any better solutions. And I found a lot of tutorials for using microcontrollers and software to solve the problem, but the hardware solutions seemed to be pretty much what I was already doing. Then I stumbled on the company Logiswitch, which has a small chip dedicated just to debouncing rotary encoders called the LS30. I impulse bought a few of them from their website and then swapped it into my test circuit. It works great and with way fewer components. Oddly enough, this chip was only just released in March of 2024, and I never would have known that if the CEO himself hadn't actually messaged me after ordering from their website. I know that sounds like a bit of a sponsorship or something, but it's totally not. I just found these chips by accident and thought they were really cool and wanted to mention them. Also, and this is totally unrelated, but these knobs feel great to turn. Alright, so finally, I have a plan. Sort of. I don't know exactly how every signal is going to connect together yet, but the rough idea is in place. Now I just need some more parts. So I'm going to have to order a bunch more chips.
They better come with dip.
Well, they're all dual inline packages, so they will. Alright, so the 2D multiplexers for the screen will need 16 outputs each, and I don't have anything like that. I'll need at least one more 555 to use in the refresh circuit, and I'll need 4 more counter chips for both the refresh and the cursor tracking circuits too. After scouring eBay, I found a lot of the parts I thought I'd need and ordered them. Unfortunately, some of the sellers were in China, and the shipping was going to take forever. Later, I talked to my friend Monty on Mastodon about how I was ordering more chips, and he offered to send a whole bunch of stuff down from Canada. The last time I checked, Canada is a lot closer to Iowa than China, so I was hopeful that his package might get here sooner. And it did! Thanks, Monty. I ended up using a bunch of these chips on the project. While I was waiting for all the parts to arrive, I started building my display. I mounted 4 of the 8x8 modules on a single large prototyping board, being careful that their orientations all matched, and then soldered them in place. That looks pretty good. I remembered that I'll need 16 horizontal and 16 vertical connections to the screen, and I didn't really want to be soldering anything directly to any chips because I'm probably going to mess it up or change my mind at some point. So I'm installing 2 long pin headers on the sides that'll become my interface to the LED grid. The left header will be the horizontal axis and the right is vertical. I didn't really think through how many wires I was going to need to connect this grid of displays together. I had to stop and test constantly and make sure everything was connected the way I thought it was. Often it was not. Soldering the screen together took so long. Well, I melted my soldering iron's USB-C cable. Luckily it's only the outer covering and I can keep working, but I'm going to take a break and order a silicone replacement. I haven't actually used a prototype board like this before, so I'm sure my soldering technique is pretty terrible. I did eventually discover a pretty good technique for connecting the wires to the pins, though. First, I strip the end and then form the wire into a tight loop using the pliers. Apply some heat and fill the loop with solder. Then position the tinned loop on the pin and then push and heat with the iron at the same time. Ta-da! Another connected wire. Only a few million more to go. It took a lot of hours, but eventually I finished it. Well, it may be ugly on the back, but the front is looking good. Did I just make a mullet? Now, after all that work, is the moment of truth. It's time to connect the screen to a pair of demultiplexers and see if I can address all of the pixels with an 8-bit address. Looks like it might work. So my plan is to refresh the display really quickly, 1 pixel at a time, and hope I can get a solid image, but I decided to run a quick test using the addressing circuit that's already working on the music box. I had to swap a few wires around, but I got it working. Unfortunately, this is about as fast as a music box can go, which is clearly nowhere near fast enough to give the illusion of a solid image. I'm a little bit more nervous now about this working out. But it looks neat though. I wanted to lock in a better board layout before I started adding much more circuitry, so I came up with this idea of sticking 2 short breadboards on the sides of the display board. This would also drastically reduce the amount of soldering I had to do. Maybe I could put the demultiplexers and rotary encoders on them and then let the rest of the logic circuits spill off the back onto a bigger breadboard. Unfortunately, the wires under the display board prevent it from sitting flush on the table, and it keeps wanting to tip over. I need a base. So I designed one in Tinkercad, and then printed it out. The good news was my measurements were pretty good. The bad news was that I couldn't get the nuts to thread onto the bolts because I didn't leave enough room to hold on to them with my fingers or a tool. It only took a few minutes to readjust the design. Unfortunately, printing it again took another 5 hours. Would you believe it if I told you that it was still wrong? Because it was still wrong. Alright, after 10 hours wasted on the base so far, I got a little bit smarter and redesigned it with a hexagon hole for the nut that would hold itself, and then test printed a much smaller piece, which only took a few minutes. Thank goodness that worked. Beautiful. It finally worked, only took 3 tries. Now it was time to start connecting the control knobs to the display. First horizontal, and then vertical. Now it's starting to feel like an Etch-A-Sketch. All it needs is to remember where I've drawn before. The first step for that is to build a refresh circuit that will sweep the screen. I'm hoping that this will be fast enough to look like a solid red image. Well, it kind of works, but not as well as I'd like. I can perceive some flicker with my eyes, but the camera really doesn't like this at all. Aha! It's a lot better in the dark. Not only does it look great on camera this way, it even looks better in person too. I wish it wasn't necessary to turn the lights off, but this works, and I'm going with it. Awesome. Now that the refresh circuit sweeps through all 256 LEDs on the screen, I just need to connect the RAM chip to those same address lines so it can read the bit that's stored in each screen position. The bit in RAM will determine if the display will show the LED for the current screen position or not during its refresh cycle. If the RAM bit is 1, then it turns the LED on. If it's 0, it leaves it off. Right now it's just showing the garbage in the RAM chip, but it's working. Earlier I glossed over a lot of stuff in this box. And if I try to explain everything I came up with in detail, including all the actual connections, this video is going to be 3 hours long. But one thing I haven't talked about yet is a part that's inside this box, and it's an 8-bit comparator. It's a chip that can check if 2 binary inputs are the same, in this case 2 8-bit binary numbers. Remember that the screen refresh circuit has 2 4-bit counters in it, but combined we could think of it as a single 8-bit number. And the control knobs also connect to 2 4-bit counters, which if combined could be another 8-bit number. So these 2 8-bit numbers are checked constantly by the comparator, and when they're the same, I know that the current screen address being refreshed is the same address of the cursor. That signal switches the RAM between read and write mode. So when the screen address and cursor position match, a 1 is written into RAM, and when they don't match, the RAM is set to read mode instead. Even better, I can easily clear the screen by more or less inverting all of this logic whenever one of the knob buttons is pressed. And just like that, I have a working electronic drawing toy that's apparently inverted. That should be easy to fix. This is really cool. It's a shame I'm so bad at drawing, but it's a lot of fun. And since the counters roll over when they overflow, you can actually wrap around the edges of the screen too. I'd like to see a real Etch-A-Sketch do that. Everyone in the house took a turn drawing. And they drew some pretty cool stuff. Not all of us are very good at it, but everyone had a lot of fun doing it. Some of these drawings are pretty good too. This project was probably way beyond my electronics skill level when I started it, but I'm really happy that I managed to pull it off anyway. All in all, it took over a month to figure out my approach and to get all the parts that I needed. It was also surprisingly expensive, although some of that was my own fault for ordering the wrong things from China. Special thanks to Monty for sending a bunch of the chips that I didn't even know I needed, and thanks to everyone who's been so supportive of this crazy endeavor in public and private. And I hope to see you again next time. Bye.